Hi everyone, welcome to tutorial 7. Our tutorial today is going to be about our midterm exam solutions. So here we are going to do all the questions that we have done in the midterm, and I'm going to do it with you and show you how to solve them. So our task 1 for today is, as you know, the hypothetical computer that stores 9 bits of information to represent numbers. So we'll start working on this in detail now in my tab where I have already written down the question again for you. So we have a hypothetical computer that stores 9 bits of information, so which basically means that we have here in the computer we have 9 bits to be stored. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Now the first bit is used for the sign of the number. So this one here is used for the sign of number, and then we have the second bit is used for the sign of the exponent here. So this one here is for the sign of exponent, and then we have 3 bits used for the magnitude of the exponent. So we have the next 3 bits here. So these are the 3 bits which is used for the magnitude of exponent. Okay, so maybe just put them in square brackets here so they don't look very mixed up. And then we have 4 bits for the magnitude of mantissa. So the next 4 bits, which is here from 6 to 9, are used for the magnitude of mantissa. Okay. Now we have to first take our number here. So this will represent the number 0.1 in the computer. So we have our number 0.1, and this is in base 10. This is a decimal number, not a binary number. So many of you got confused when you saw 0 and 1. You thought it as binary. Base 2, no, this is a decimal number of base 10, and we have to make this 2 binary number. So we have to represent this in floating point representation. So we have to represent this as a number. So for the whole part we have something, then we have the radix point, then for the decimal part we have some binary number in base 2, and then we will be having, let's not say about the power now. Okay, so this is what we are supposed to do, right? So we know that the whole number is 0 here, so we can just write here a 0 because 0 in binary is just 0. And then for the decimal part we have 0.1, so we have to make the 0.1 to binary, right? So the 0.1, you can write it as 0.1. To make it binary, we have to multiply it every time by a 2. So here we have 0.1 times 2, which is 0.2, and then we have here we take let me maybe write this a bit down. So here, yeah, so we have 0.1 times 2, is equal to 0.2, and here I'll write the integer part. So the integer part here is the 0, so that's 0 here, and the decimal part is 0.2, so we'll use that again. So 0.2 times 2 is 0.4. Again, we have the integer part is just 0, and then we have 0.4, so 0.4 times 2 is equal to 0.8, and as you can see, the integer part is 0 again, and we have 0.8 times 2 is equal to 1.6. So now we have 1 as the integer part, and we have 0.6, that's this part here, 0.6 times 2, which will give us 1.2. So we take the integer part here and write it down, and we have then 0.2, so 0.2 times 2 is equal to 0.4. So we have 0, the integer part, and 0.4 times 2 is equal to 0.8. Then we take the integer part 0, and then we have the 0.8 here, so we have 0.8 times 2 is equal to 1.6. So the integer part is 1, and then we have 0.6. So you can see that it's repeating, right? So 0.4, 0.8, 1.6, or you can say here 0.2, 0.4, 0.8. We have already seen it, so it's repeating, and again we'll continue from 0.6 times 2, so it'll again repeat these steps here. So we can just stop here, and we can say that this continues, right? So now we can write it down here. So I will try to fill it up in here. We have 3 zeros, 1, 2, 3, 4, sorry, 3 zeros. So we take this from top to bottom. So we have 3 zeros, then we have 2 ones, again 2 zeros, and a 1, and it continues. Of course, you need infinite number of bits to represent 0.1, so we can continue doing it as long as we want, or we can stop. And here we have this in base 2, right? Okay, now we have represented the decimal number in an approximate binary number, and what we're supposed to do now is to represent this in floating point representation form, right? So if you want to do now, or if you want to say, let's say if you want to represent this number here, which is 0.000110001, if you want to represent this one here in floating point, what we have to do is we have to take the decimal to a place where the number before the decimal should be non-zero. So if we take it here, the number before the decimal will be 0. So if we take it here, still it is a 0. If we take it here, still the number before the decimal is a 0. So we have to take it here, and then we see that the number before the decimal is now 1. It's a non-zero number, right? So then we are going to represent this in the floating point representation format. So here we have now 1.1001, right, in the base 2. And now because you have shifted the decimal 1, 2, 3, 4 steps, so you have here 2 to the power minus 4, right? If you shift it towards your right side, you get a minus or negative power. So now here we have minus 4 in decimal numbers. This is to base 10, right? So we have to make this to base 2 also. So let's make minus 4 to binary. So this is in base 10 and we have to make it to base 2. So what we can do is we can take minus 4 divided by 2, we get minus 2. The quotient and the remainder is 0, and then we have minus 2 divided by 2, so you have here minus 1. The quotient and the remainder is again 0, and then you have minus 1 divided by 2, and this time you have quotient is 0, or you can say minus 0, and the remainder is 1. So we stop here and we take these numbers bottom up now. So we can just keep the negative sign here. You could also not use this minus here. Actually, you could just take the 4 and work it out, and here keep the minus sign out here, and we have 1 0 0 in decimal in binary numbers to represent 4, right? So now we can finally represent the floating point representation as 1.1001 to the base 2 times 2 to the power minus 100, and this is also base 2 now. Okay, so now we have to see that we are given for the magnitude of mantissa 4 bits, right? So after our radix point here, we should have only 4 numbers here. If you have more than 4, you can just delete them, and if you have less than 4, then you most probably should work more steps here, right? You should work out more steps here. So many of you in the midterm have stopped at a very early stage here, like you have done till here or something, which is not right, because you need 4 digits for your mantissa here, right? So keep that in mind and work it out. So now let me rewrite this here. So we have our number 0.1 in base 10, and in floating point representation it is represented as 1.1001 base 2 times 2 to the power minus 100, or it's not 100, it's 100 in base 2. So this is the floating point representation of the number, and now we can easily write how it is represented in the computer. So let's draw our table again. And here we have, as we know, the first 2 bits are for the sign bits. So this is for the sign of the number, and the number is positive, so it is 0. And this n here is for the sign of the exponent, and as we can see, our exponent is a negative number, it's minus 4, so here it will be 1. And then we have 3 bits for the exponent. So here we have exponent as 100, so we already have our 3 bits, so we'll have here 1 0 0, and then we have 4 bits. So yeah, we can just delete this part here. So we have 4 bits here for the magnitude of the mantissa. So for the magnitude of the mantissa, we take the 4 bits after the radix point. So these are the 4 bits that we need to fill it up in. So after the radix point, we have 1 0 0 1. So that's the way 0.1 will be represented in computer.